operations. So first of all, a huge advantage of linked lists is that we can insert items at the beginning of the data structure quite fast in order one running time complexity because we just have to update the references. Okay, so for example, if we want to insert 5, then this is going to be the first item. It is pointing to a null at the beginning. Then what if we would like to insert -2? Then -2 is going to be the first node in the data structure and it is going to point to number 5. Okay, what if we would like to insert 10? Then 10 is going to be the first item of the data structure and we just have to handle the references. It is pointing to the previous first item of the data structure, -2. Then for example, we can insert value 2 and after the insert operation, it is going to be the first item of the linked list data structure. So inserting new items at the beginning of the linked list is extremely fast. We can do it in order 1 constant running time complexity. You may pose the question why? Because this is exactly how we designed the structure of linked lists. So this is what we have been talking about in the previous lecture, that we store a reference to the first node in the data structure. This is the so-called head node. So every other item can be accessed starting with the first node. So of course, if we want to insert new items at the beginning of the linked list data structure, then we have to manipulate the first node, so basically the head node. And because we have access to that given node, we can update the pointers in order 1 constant running time complexity. So this is why manipulating the first item of the linked list is extremely fast. Okay, so this is exactly what's happening here. Then what if we would like to remove a given item from the beginning of the list? Again, because we have a reference to the first node, the so-called head node of the linked list, again, it is going to be quite a fast operation. It can be done in order 1 constant running time complexity. So if we want to remove the head node, so value 2, we just have to remove it and the new head node, so the first node of the data structure, is going to be updated to be 10. What if we would like to remove 10? Of course, we just have to remove it, and of course the head node is going to be -2. What if we would like to remove -2? Then 5 is going to be the head node. So basically, because we have an active reference to the first node of the data structure, of course we can update the first node of the data structure quite fast. This is exactly why we store a reference to the head node. Of course, there are slow operations as well, as far as linked lists are concerned. For example, if we want to insert a new item at the end of the linked list, or basically if we want to insert a new item to an arbitrary location, what do we have to do? We have to start with the head node, so the first node of the linked list, because this is the node we can access. We can access the head node exclusively. We are not able to access the middle node. We are not able to access the last node. This is the topology of the linked list data structure. We can access the first node exclusively. So we have no other option but to start with the beginning. It is not the last node because we know for certain that the last node is pointing to a null. So we keep going. 10 is the last item. Of course not. We keep going. -2 is the last item. Of course not. We keep going. 5 is the last item. So we have to insert 19 to be the last item of the data structure. And if we want to insert a new node, so we know the location, then it is a fast operation. We just have to update the references. 5 is going to be pointing to 19, 19 will be pointing to a null. Of course it is fast. What's extremely crucial, that the slow operation is to find the given node. So we have to find the item we want to remove or we want to insert with a linear search in order and linear structure. And of course it is the same if we want to remove an arbitrary item. For example, if we want to remove the number 5, then what do we have to do? We have to start with the first node and we have to looking for that item, so we have to consider the next node in the linked list data structure until we find the item we are looking for, and then we can remove it again. We just have to update the references. It is fast. What makes it slow is that first we have to traverse the linked list on a one-by-one basis. So this is why linked lists are working extremely fine if we want to update or manipulate the first item. But if we want to update or manipulate the last item or an arbitrary item, then the running time complexity is going to be linear, which is not that good. We can do better. This is exactly why we are going to talk about binary search trees. Okay, so we can come to the conclusion that if we want to manipulate the first item, whether we want to insert or remove the first item, it is extremely fast. It has order 1 constant running time complexity. This is exactly why we like linked lists. But what if we would like to manipulate arbitrary items? For example, the last item of the data structure, whether we would like to insert a new item or we would like to remove an existing item. it's going to have ordo and linear running time complexity, which means that if we have to do several of these operations, then linked list is not the best option possible. Okay, so let's talk about the advantages and disadvantages of linked lists. Linked lists are dynamic data structures. They can acquire memory at runtime by inserting new nodes. So what does it mean? There is no need for resizing the data structure as we have seen with arrays. And it is absolutely crucial that this data structure can grow organically. It is absolutely not a problem if we do not know the size of the linked list at compile time. We are able to insert new nodes without any problem in ordo 1 constant running time complexity. It is not the same as we have seen with arrays. As far as arrays is concerned, we should know the number of items we will have to store, because otherwise we have to resize the array, which is quite an expensive operation with ordo and linear running time complexity. Manipulating the first item of a linked list is extremely fast, and what's crucial that we can store items with different sizes. Arrays assume that items have the exact same size, and it is not true with linked lists. So linked lists are dynamic data structures, while arrays are static data structures. What about the disadvantages? Of course, because we have to store the references or the pointers, we need more memory. The most important disadvantage is that there is no random access. As far as one-dimensional arrays or multidimensional arrays are concerned, we like random accessing. This is why we can achieve ordo 1 constant running time complexity, and it is not true for linked lists. The items in a linked list are stored in different locations in the memory, which means that we are not able to use random access. We can access the first node or the head node of the linked list exclusively. What's extremely crucial that we are not able to go backwards. So a good question is how to get to the previous node. So for example, if we are considering node 5, then how to get back to node -2? Because of course the reference is pointing from -2 to 5, but of course we are not able to go back from 5 to -2. And basically this is why we are going to talk about doubly linked lists, because doubly linked lists can handle this problem. Okay, and we still haven't solved the main issue, how to search for arbitrary items faster than ordo and linear running time complexity. So no matter we are using arrays or linked lists, if we want to search for an arbitrary item, then the running time complexity will be linear, and of course we can do better. This is why we will consider binary search trees. And another crucial disadvantage of linked lists, and by the way it is true for arrays as well, is that these data structures are not predictable. So what does it mean? The running time of the application relies extremely heavily on the operations the user do. This is exactly what we have been talking about. If we want to manipulate the first item, it is a fast operation. If we want to manipulate an arbitrary item, then it is a slow operation. So basically, if we have an application that can have constant running time complexity as well as linear running time complexity, depending on what the users do, of course, it is not a good application. For example, let's consider Facebook. You would like to search for a given friend. Of course, Facebook has to handle this problem if a given user tries to find another user of the application. If we have, for example, a linked list data structure, in this case it takes ordo and linear running time complexity to search for an arbitrary item, which means that we will end up waiting 10 to 20 minutes for Facebook to find the relevant user we are looking for. And of course, it is not a good user experience. The user is going to remove the application and so on. So it is absolutely crucial that we like applications where the running times of the given operations are approximately the same. And this is exactly why binary search trees came to be. Approximately all the operations have ordo, log, and logarithmic running time complexity. It is not going to depend on what operations we do. Whether we are searching for the first item, the middle item, or the last item, all the operations are predictable. So I don't want to repeat myself over and over again, but predictability is an absolutely important feature of an application. Thanks for watching.